Alright, silly people, here's the situation. This time we have two eigenfunctions, f and g, which happen to share an eigenvalue, um, q, lowercase q, when operated on by the operator big Q. Um, and the first thing that we need to prove is that if we had a linear combination, any linear combination of f of x and g of x, um, that linear combination would also have the same eigenvalue of lowercase q. And so we're going to do it like this. We're going to say we define a eigenfunction called h of x. That's going to be just alpha f of x plus beta g of x, where alpha and beta are literally any complex number ever. And we're going to operate q on it. So q h of x, which when you expand it out, it is q, alpha q f of x plus beta q g of x. And then just referring to the problem statement up here, we can evaluate both of those. So that's alpha lowercase q f of x plus beta lowercase q g of x, which we can group it together to be q times alpha f of x plus beta g of x. In other words, q times h of x, which that is the eigenvalue eigenfunction equation right there. So that works. The next bit of the problem is to, let me actually read it. Check that f of x equals e to the x. So f of x equals e to the x, and g of x equals e to the minus x. Are eigenfunctions of the operator d squared dx squared. Okay, and they both have the same eigenvalue. Okay, I can show that. So just acting q on f of x now, it'll be d squared f dx squared. The first derivative is just going to be 1 times e to the x, and then the second derivative is going to be 1 times e to the x, so that's done. And then q acting on g of x is d squared g dx squared is the first derivative of minus e to the x, minus x I should say, and then the derivative of that is minus minus and a plus e to the minus x. Okay, so clearly they both did end up having the same eigenvalue, but that eigenvalue happened to be 1. Okay, so that's chill. The next bit of the problem is to find two linear combinations of f of x and g of x that they both have the same eigenvalue, obviously, because any linear combination does. But I want to find two linear combinations that are orthogonal on the interval minus 1 to 1. So it has to be the case that the integral dx from minus 1 to 1 of f of x, or I'm going to say h1 of x, h2 of x equals 0. And that's just another fancy way of writing inner product of f with g, right? Or h1 with h2. Okay. So I'm going to say that I choose h1 of x just to be a f of x plus g of x, and h2 of x equals f of x minus g of x, and I'll show you that this works. And so, again, it's going to be the integral from minus 1 to 1 of, and then f of x was just e to the positive x plus e to the minus x. h2 of x will be e to the x minus e to the minus x. That has to be integrated dx. So we can distribute what's in the parentheses. We'll get e to the 2x minus 1 plus 1, and then minus e to the minus 2x, I think. Yeah. So the 1's will cancel out, but we do have to do the integrals that are left over, which is dx e to the 2x minus the integral minus 1 to 1 dx e to the minus 2x. These both integrals are both pretty chill. This is e to the 2x over 2. From minus 1 to 1, this is minus e to the 2x over 2 from minus 1 to 1. And then evaluating at the endpoints, we have e squared over 2 minus e to the minus 2 over 2 minus minus e to the minus 2 over 2 plus e to the 2 over 2. And then we can distribute those subtractions there. So this is plus e to the minus 2 over 2 minus e squared over 2. So this cancels out this cancels out that, and it is in fact 0. So it was a good guess. Alright. Oh, and by the way, if anybody's been paying attention, I moved back to this place where I've been recording my old videos because I was getting really tired of the wobbly table that I've got over there that I've been recording the last couple on. So if you liked that background, my bad. I just like this one more, and I'm not willing to change. Alright.